Identities with complex numbers. As we talked about in our previous lecture, we were talking about when we have difference of squares, a squared minus b squared, which when we factor out is a plus b times a minus b. X squared minus 9 is factored out is x plus 3 times x minus 3. 4y squared minus 64 is 2y plus 8, 2y minus 8. 16z squared minus 36 is 4z plus 6, 4z minus 6. Because those two central components cancel each other out, are in a FOIL, the O and the I, we do the same thing with imaginary numbers. X plus I times x minus I gives us, interestingly enough, x squared minus I squared. And remember, I squared is negative 1. So x squared minus negative 1 is the same as x squared plus 1. And we can do a lot with this, especially looking at to its most basic levels of where something zeroes out on the imaginary and real plane. Now, as I said, I showed before how we got x minus I times x plus I is x squared plus ix minus I squared, which is x squared minus I squared. And again, I squared is negative 1, so it's x squared minus negative 1 x squared plus 1. Knowing this, we can factor two perfect squares that are added to each other down into the imaginary components. Let's look at x squared plus I squared. And this is the base of what we're going to do today. X squared plus I squared is the same as x squared minus negative 1 y squared. Instead of plus squared, I got minus a negative 1. Because this is the same as x squared plus 1y squared. So all I've done is rename this as x squared minus negative 1y squared. Now, I got negative 1 right here. Well, I'm going to change negative 1 to negative I squared. And then here's my y squared. So if I rewrite this, this is now x squared minus 1y squared. And now I have a difference of squares. This is x plus iy and x minus iy. We just done a reverse what just showing on the previous slide. Let's look at a real life example with this. 36 a to the 8th right here and 2b to the 6th. Well, since I have even exponents, I know I can have these and separate them out. 36 a to the 8th is the same as 6 a to the 4th squared, because 6 squared is 36. And remember, when we multiply exponents around the parentheses, a to the 4th to the 2nd is a to the 8th. 4 times 2 is 8. And the reason is a to the 4th times a to the 4th. If we just multiply it out normally, it's still got a base of a. And remember, we add exponents. So it's a to the 8th. So 36 a to the 8th is the same as 6a to the 4th squared. And there's my first square. Just renamed it. Then I got my second one here, 2b to the 6th. Well, we could separate this out. Instead of 2b to the 6th, square root of 2b to the 3rd. The square root of 2 times b cubed, because I multiply this out, times square root of 2 times b cubed. Be a little bit better there. Here's my b cubed times b cubed is b to the 6th. And square root of 2 times square root of 2 is square root of 4, which is 2. So now all I've done is I've just rewritten this as two squares. Instead of 36a to the 8th, it's 6a to the 4th squared, plus, instead of 2b to the 6th, it's square root of 2b to the 3rd squared. And now I'm going to, instead of this plus, I'm going to make this minus a negative 1. Because we already know there's a 1 up here, we just never say it. But instead of plus 1 times square root of 2b to the third squared, I'm just making this minus a negative 1. Well, now, like I said, minus negative 1, negative 1 is I squared. And now, if I put this I squared on the inside, it would be I right here, and then there's a square on the outside. So it's actually rewritten as 6a to the fourth squared, which is what we've got in the beginning here. And now it's I squared of 2 times b cubed all to the squared. And now what I have here, I have a difference of squares. So it's going to be 6a to the fourth plus I2 to the b cubed, and then 6a to the fourth minus I times square root of 2b to the cubed. And really all I'm doing is instead of doing this plus here, is that's a plus 1. We just never say there's a 1 in front of it, but it is there. I'm making this minus a negative 1, which is the same as plus 1. And now that I've got a minus a negative 1, minus and negative 1 is I squared. And this right here allows us to separate out and make difference of squares to its most basic level. We can do this with generalized higher exponent functions as well. X to the fourth plus x squared plus 9, if I just factor this out, and this is not really that difficult at all. If it was x squared plus 10x plus 9, it'd be x plus 9 times x plus 1. But it's x to the fourth plus 10x squared plus 9. And I can factor this out as x squared plus 9 times x squared plus 1. X times x squared times x squared is x to the fourth. There's my first. And then my outside is x squared plus 1. And then my inside is 9 times x squared. That's 10x squared right there. There's my O and I. And then 9 times 1, it's very last. That's my last, is 9. So I've just let me erase this now. I've just factored all this out. X to the fourth plus 10x squared plus 9. And I factored it down to its simplest levels. But I'm not done. I would actually like to get this down to the most basic levels. Because if I'm doing on a complex plane, I want to know where it zeroes out. And I don't have any zeroing out here in a real plane because there's nothing that can subtract a 9 that's squared. Unless I have an imaginary number. And that's what we can do right here. Same thing with this one. So I'm going to rewrite this. I'm going to write both of them actually as complex numbers. On one side, I got x squared plus 9. On the other side, I got x squared plus 1. Let's factor this out. X squared plus 9 is the same as x squared minus negative 9. And there's my x1 minus. And I'm going to change, that's the same as negative x squared minus negative 1 times 9. Well, there we go. Here's my negative 1, which is the same as I squared. So now it's x squared minus I squared times 9. And what I got here is x squared minus 9I squared. Well, that ends up being the difference of squares right there. X plus 3I, x minus 3I. And on the right side, where I got my x squared plus 1, that's the same as x squared minus negative 1. Well, there's my minus, and remember, negative 1 is I squared. So there's my x squared minus I squared. And that ends up being x plus I and x minus I. So when I factor this out to its most basic, simplest form, and I can't do it on the Cartesian plane, but I can do it on the complex number plane, it's going to be x plus 3I times x minus 3I times x plus I times x minus I. Multiple areas where it will factor out to its most basic level. Let's do one last one here. And this one looks a little hairy, but it really isn't that bad. I've got 2x to the 6 plus 4x to the fourth minus 30x squared. Well, the first thing I'm going to do is I'm going to factor out a 2x squared. And that makes this a lot simpler. Because if I factor out 2x squared of all this, that leaves an x squared. There's x squared times 2x squared times x to the fourth is 2x to the sixth. If I factor 2x squared out 4x to the fourth, that leaves 2x squared. And then 2x squared goes into minus 30x squared 15 times. So basically what I've done here is I've just factored out 2x squared. And that'll be a 0 if I want to get to the 0 point for that x. But I'm left with, when I do basic PQ method, x squared, x to the fourth plus 2x squared minus 15 is going to be x squared minus 3 times x squared plus 5. X times first x times x, x to the fourth. On the outside, x squared times 5 is 5x squared. Then 3 on the inside, 3 minus 3 times x squared is minus 3x squared. 5x squared minus 3x squared is still plus 2x squared. And then negative 3 plus 5 equals minus 15. So erase my pen marks here to make it a little easier for everyone to see and understand what I am doing in all this madness. And there's a method to it, actually. So now that I factored out, I got my 2x squared out. I was going to leave this alone here. But I got x squared minus 3 and x squared plus 5. Well, here's a difference of squares right here. It's an interesting difference of squares. We didn't have to do the convert into a complex number. X squared minus 3. I can learn almost anything if subtracting. This is the same as x plus square root of 3 plus x minus square root of 3. Because x times x is x squared. X times minus 3 is minus square root of 3x. Square root of 3 times x plus 3x. Those two cancel each other out. And then square root of 3 times square root of negative square root of 3 is negative 9. Square root of 9. Negative square root of 9, which is 3. So this one can be factored out. X plus square root of 3, x minus square root of 3. I've just made a difference of squares by turning that minus 3, that 3 into a square root of 3. But on the other side, we're going to use our imaginary number component. X squared plus 5. That's the same as x squared minus negative 1 times 5. Because minus negative 1 is the same as plus 1. So it's x squared plus 5. But now I've just renamed it as minus negative 1 times 5. Well, negative 1, as I said before, is I squared. So there's my minus here. And it's going to be x squared minus 5i squared. I got a difference of squares, so to speak. If I take the square root of 5, it's going to be x plus square root of 5 times I times square root of 5 and x minus I times square root of 5. And in the end, this whole equation on its most basic level is right here. Here's my 2x squared I factored out. Let me erase all this again. Okay, sorry. Okay. And I factored out my 2x squared in the very beginning. This is my x plus 3, my x plus square root of 3 to x minus square root of 3 right here. Made difference of squares. And then I converted this x squared plus 5 into x plus I square root of 5 plus x minus square root of 5. And we've got down to the most basic, simplest components.